Hello again. Let's continue with shortest remaining time first scheduling algorithm. We already emphasized that shortest job first algorithm can be preemptive or non-preemptive. This choice arises when a new process arrives at the ready queue while a previous process is still executing. The next CPU burst of the newly arrived process may be shorter than what is left of the currently executing process. A preemptive shortest job first algorithm will preempt the currently executing process, whereas a non-preemptive shortest job first algorithm will allow the currently running process to finish its CPU burst. Preemptive shortest job first scheduling is sometimes called as shortest remaining time first scheduling. As an example here, consider the following four processes with the length of the CPU burst given in milliseconds. Process P1, burst time 8, arrival time will be 0 for that. We have P2 with the arrival time 1 and burst time 4 milliseconds. We have P3 with the arrival time 2 and burst time 9 milliseconds. And at last, we have P4 with the arrival time 3 and burst time 5 milliseconds. If the processes arrive at the ready queue at the times shown in this order and need the indicated burst times, then the resulting preemptive shortest job first schedule will be like that in that Gantt chart. At the time 0, we have process 1. Process P1 is started at time 0, since it's the only process in the queue, because at the time 0, we have just P1. So independent from the burst time, we have to start to execute P1 because it's our only process. So process 1 is started at time 0 since it's only process in the queue. But process P2 arrives at time 1. We executed P1 1 milliseconds, but 1 millisecond. After that, P2 arrived the ready queue. The remaining time for process 1 will be 7 milliseconds. Okay, burst time for process 1 was 8 milliseconds, but we already executed 1 millisecond that process. So that means the remaining burst time for process 1 will be 7 milliseconds. So the remaining time for process 1 is larger than the time required by process 2, because process 2 needs 4 milliseconds as burst time. So process 1 is preempted and process 2 is scheduled. So here at time 0, we have just P1, so we have to start it with P1. At time 1, let's say after 1 milliseconds, P2 arrives at ready queue, and P2's burst time is 4, but the remaining job for P1 is 7. So P1 is shorter than the remaining part of P1. So we are going to preempt P1 from the CPU, and we are going to start to execute P2. At time 2, P3 will arrive the ready queue, but the remaining time for P2 will be shorter than P3, so we are going to continue with P2. At time 3, P4 will arrive the ready queue, but still the remaining part of P2 will be shorter than P4, so we are going to continue with P2. At 5th millisecond, here we are going to take a look at the remaining jobs. The burst time for P1 will be 7, for P3 it will be 9, and for P4 it will be 5. So that means we are going to continue with P4 and then P1 and then P3. So the average waiting time for this example, it will be 10 minus 1 for P1. Okay, because it starts in the 10th millisecond here, but we already executed P1 1 millisecond. So the waiting time for P1 will be 10 minus 1. The waiting time for P2 is 0 because it starts at the first millisecond, but it also arrived the queue at the first millisecond. So the waiting time for P2 will be 1 minus 1. The waiting time for P3 will be 17 minus 2 because it starts executing on 17, but it also arrived the queue at second millisecond. So the waiting time for P3 will be 17 minus 2. And the waiting time for P4 will be 5 minus 3. It starts to execute at 5, but it arrives the ready queue at 3, so it just waits 2 milliseconds. So based on that, the average waiting time using the shortest remaining time first scheduling algorithm on this set of processes will be 6.5, as you can see from here. So if we use a non-preemptive shortest job first scheduling algorithm, it will result in an average waiting time of 7.75 milliseconds. So the shortest remaining time first algorithm will give us an optimal average waiting time when we compare it to non-preemptive shortest job first scheduling algorithm. Any question? So in here, instead of the total amount of burst times, we are comparing the remaining time. If the remaining time of the, let's say, assume that a new process enters the ready queue, and I'm already executing a process with the, let's say, burst time 8. But at some point, a new process entered the ready queue, and its burst time is shorter than my remaining time. So in that case, I'm going to preempt my process from the CPU, and I'm going to execute the newly coming process. So it's called as shortest remaining time first. The next one is round robin. The round robin scheduling algorithm is similar to first come first served scheduling, but here we have a preemption. Preemption is added to enable the system to switch between processes. A small unit of time, called in this case as time quantum or time slice, has to be defined. So based on time quantum, we can switch between processes. A time quantum is generally from 10 to 100 milliseconds in length. The ready queue is treated as a circular queue. The CPU scheduler goes around ready queue, allocating the CPU to each process for a time interval of up to 1 time quantum. To implement round-robin scheduling, we again treat the ready queue as a first in, first out queue of process, similar to a first come, first served scheduling algorithm. New processes are added to the tail of the ready queue. The CPU scheduler picks the first process from the ready queue, sets a timer to interrupt after 1 time quantum, and dispatches the process. If there are n processes in the ready queue and the time quantum is q, then each process gets 1 over n of the CPU time in chunks of at most q time units. Each process must wait no longer than n minus 1 times q time units until its next time quantum. For example, with 5 processes and a time quantum of 20 milliseconds, each process will get up to 20 milliseconds every 100 milliseconds. So we can guarantee that situation. The performance of round-robin algorithm, of course, depends on the size of the time quantum. At one extreme, if the time quantum is extremely large, the round-robin policy is the same as first-come, first-served policy. In contrast, if the time quantum is extremely small, let's say 1 millisecond, the round-robin approach can result in a large number of context switches. In every 1 millisecond, you have to make a new context switch. Here we have an example. Consider the following set of processes that arrive at time 0. The length of the CPU burst given in milliseconds, P1 is 24, P2 is 3, and P3 is 3. So if we use a time quantum for 4 milliseconds, then process 1 gets the first 4 milliseconds. Since it requires another 20 milliseconds, it's preempted after the first time quantum, and the CPU is given to the next process in the queue, which is process 2. Process 2 does not need 4 milliseconds. Okay, our quantum is 4 milliseconds. We can serve 4 milliseconds for every process, but P2 just needs 3 milliseconds. So P2 does not need our 4 milliseconds, so it quits before its time quantum expires. It's already terminated, so we have to make a context switch at that point. And then the CPU is given to the next process, which is process 3. Again, here process 3 does not need 4 milliseconds. After 3 milliseconds, process 3 will be terminated, and then we are going to return the process 1. We are going to execute process 1 for 4 milliseconds, and then we are going to check the ready queue. If there's a new process, we are going to continue with that. But in this case, we have just 3 processes, and P2 and P3 has terminated on their first quantum, so we have just P1. So for all quantums, we are going to execute P1 for the next periods. So the resulting round robin is something like that. Let's calculate the average waiting time for this schedule. P1 waits for 6 milliseconds, because actually here it starts with the 10 milliseconds, but it already executed for 4 milliseconds. So that means the waiting time for P1 is 10 minus 4, so it will be 8 milliseconds. P2 waits for 4 milliseconds and P3 waits for 7 milliseconds. So the average waiting time here will be 5.66 milliseconds. Okay, so this is how you can find the average waiting time for round-robin algorithm. But again, the most important part of the round-robin algorithm is the selecting the time quantum. In this case, we choose the time quantum as 4 milliseconds. So let's assume that we choose the time quantum as 24 milliseconds. So we are going to start with the P1, and we are going to give 24 milliseconds for each process. So that means we are going to execute P1 for 24 milliseconds. At that point, P1 will be terminated, and then we are going to execute P2 and P3. So if we give an extreme quantum like that, this algorithm will work like first come, first served algorithm. If we make the time quantum, let's say 1 milliseconds, that means we are going to execute P1 1 milliseconds, and then P2 1 milliseconds, and P3 1 milliseconds. In that cases, we select the time quantum as 1 millisecond. So that means P2 and P3 does not terminate it in their own quantum. And then we have to make that operation again. P1, P2, P3, P1, P2 will be terminated in that point, and P3 will be terminated and that at that point. In that point, after that, we can continue with the P1. So as you can see, instead of 3 context switches here, we made 9 context switches if we use time quantum as 1 millisecond. And we already know that making context switch is a costly operation. Okay, we said that If the time quantum is extremely small, let's say 1 millisecond again, the round-robin approach can result in a large number of context switches. Assume, for example, that we have only one process of 10 time units. If the quantum is 12 time units, the process finishes in less than one time quantum with no overhead. If the quantum is 6 time units, however, the process requires 2 quanta, resulting in a context switch. If the time quantum is 1 time unit, then 9 context switches will occur and it will slow the execution of process accordingly. Thus, we want the time quantum to be large with respect to the context switch time. If the context switch time is approximately 10% of the time quantum, then about 10% of the CPU time will be spent in context switching. In practice, most modern systems have time quanta ranging from 10 to 100 milliseconds. The time required for a context switch is typically less than 10 milliseconds. So the context switch time is a small fraction of the time quantum in our modern operating systems. And again, it's the most important point of the selecting the proper time quantum on round-robin algorithm. Turnaround time also depends on the size of the time quantum. As we can see from this figure, the average turnaround time of a set of process does not necessarily improve as the time quantum size increases. In general, the average turnaround time can be improved if most processes finish their next CPU burst in a single time quantum. Although the time quantum should be large compared with the context switch time, it should not be too large. As we pointed out earlier, if the time quantum is too large, round-robin scheduling degenerates to an first-come, first-served policy. So we have a general rule for that. It's a rule of thumb is that 80% of the CPU burst should be shorter than the time quantum. So we have a general knowledge of the general burst times of CPUs because we have detailed statistics. Based on that statistics, we can select the proper time quantum while designing the round-robin algorithm. So the general rule, 80% of the CPU burst should be shorter than the time quantum. So that means 80% of your processes will be completed, will be terminated in just one quantum. So your round-robin algorithm can work effectively in that way. Okay, let's continue with priority scheduling. Actually, the shortest job first algorithm is a special case of the general priority scheduling algorithm. A priority is associated with each process and the CPU is allocated to the process with the highest priority. Equal priority processes are scheduled in first-come, first-served order. A shortest job first algorithm is simply a priority algorithm where the priority is the inverse of the next CPU burst. The larger the CPU burst, the lower the priority, and vice versa. Note that we discuss scheduling in terms of high priority and low priority. Priorities are generally indicated by some fixed range of numbers, such as 0 to 7 or 0 to 5. However, there is no general agreement on whether 0 is the highest or lowest priority. Some systems use low numbers to represent low priority, but others use low numbers for high priority. In some systems, 0 will be lowest priority. In some systems, 0 will be highest priority. So this difference can lead some confusion. In this text, in this course, we are going to assume that low numbers represents high priority. If the number is large, the priority will decrease. So 0 will be highest priority in this case. Priority scheduling can be, again, preemptive or non-preemptive. When a process arrives at the ready queue, its priority is compared with the priority of the currently running process. A preemptive priority scheduling algorithm will preempt the CPU if the priority of the newly arrived process is higher than the priority of the currently running process. A non-preemptive priority scheduling algorithm will simply put the new process at the head of the ready queue. A major problem with priority scheduling algorithm is indefinite blocking or starvation. A process that is ready to run but waiting for the CPU can be considered as blocked. A priority scheduling algorithm can leave some low priority processes waiting indefinitely. Because let's assume that we have a ready queue, we have a newly arriving process all the time, and all new processes priority is higher than one of the current process. So instead of executing that process, we have to execute higher priority processes so that our low priority process will be blocked in our ready queue. So a solution to the problem of indefinite blockage of low priority process is aging. Aging involves gradually increasing the priority of process that wait in the system for a long time. For example, if priorities range from 127, which is low, to 0, which is high, we could periodically, say in every second, increase the priority of a waiting process by 1. Eventually, even a process with an initial priority of 127 would have the highest priority in the system and would be executed. It's called as aging. In fact, it will take a little over 2 minutes for a priority 127 process to age to priority 0 process. So it's a solution for starvation. Here we have an example. As an example, consider that this set of processes assumed to arrive at time 0 in order to P1, P2, P3, P4, P5, and their burst times are 10, 1, 2, 1, and 5 respectively. And we have priorities attached for every process. The priority of process 1 is 3, process 2 is 1, process 3 is 4, process 4 is 5, and process 5 is 2. We said that the lowest number will be highest priority in our case. So using priority scheduling, we will schedule these processes according to this following chart, this Gantt chart. The highest priority, actually P2 has the highest priority, so we have to start with the P2. After that, which burst time is 1. So after that, after 1 millisecond, we have to pick a new process from our ready queue, and we are going to check the priorities. So we can directly see that the next priority will be P5, and we are going to execute P5. After 5 milliseconds, we have to pick another one. In that case, again, we are going to check the priorities, and the lowest number will be highest priority, and we are going to get the process with the highest priority and execute that process. So using this priority scheduling with this set of processes, the average waiting time will be 8.2 milliseconds. Another option is to combine round-robin and priority scheduling in such a way that the system executes the highest priority process and runs process with the same priority using round-robin scheduling. Let's illustrate with an example using this set of processes with the burst time in milliseconds, P1 4, P2 5, P3 8, P4 7, and P5 3 milliseconds. And their priority 3 for P1, 2 for P2, 2 for P3, 1 for P4, and 3 for P5. So the P4 has the highest priority. So we have to start with the P4. We don't have another processes that prior than P4. So after the termination of P4, we are going to select a new process. But in that level, P2 and P3 has the same priority. So we are going to start with P2, but instead of the waiting of termination of P2, we are going to use a round robin algorithm here. If we have processes with the same priority, based on a time quantum, we can create a round robin. So P2 and P3 has the same priority, so I'm going to execute P2 for 2 milliseconds and then P3 for 2 milliseconds, again P2 for 2 milliseconds, P3 for 2 milliseconds, and so on. At some point, both of them will be terminated, their task will be done, so I can move on the next level of priority. At that point, I have P1 and P5, they have both in the priority 3, so again, I can create a round robin between just P1 and P5. And that's it. That's the that's a combination of using priority scheduling with round robin. Still, we are using priority scheduling. The highest, if the process has the highest priority, we have to start the execution of that process. But if we have more than one process at the same level, instead of creating a first come first served scheme on that level, we can use round robin between the same level of processes. Is that clear? Any question? With both priority and round robin scheduling, all processes may be placed in a single queue, as you can see here. And the scheduler then selects the process with the highest priority to run. Depending on how the queues are managed, an ON search may be necessary to determine the highest priority process. Okay, we have a queue and we want to find the highest priority. So based on your queue, you have to make a search on that queue to find the highest priority. So depending on how the queues are managed, and ON with the complexity ON, search may be necessary to determine the highest priority process. In practice, it's often easier to have separate queues for each distinct priority, and priority scheduling simply schedules the process in the highest priority queue. So instead of finding the highest priority on the same queue, we can create different queues for different priorities. So your scheduler starts with the highest priority queue, and then if we don't have any process on that level, we can move the next queue, as you can see in this figure. This approach, known as multi-level queue, also works well when priority scheduling is combined with round robin. If there are multiple processes in the highest priority queue, they are executed in the round robin order. In the most generalized form, form of this approach, a priority is assigned statically to each process, and a process remains in the same queue for the duration of its runtime. A multi-level queue scheduling algorithm can also be used to partition processes into several separate queues based on the process type. Not only the priority, also we can use process types for that. For example, a common division is made between foreground or interactive process and background or batch processes. These two types of processes have different response time requirements and so may have different scheduling needs. Separate queues might be used for foreground and background processes, and each queue might have its own scheduling algorithm. The foreground queue might be scheduled by a round-robin algorithm, for example, while the background queue is scheduled by a first-come, first-served algorithm. Let's look at an example of a multi-level queue scheduling algorithm with 4 queues listed based on the priority. From highest to lowest, we have real-time processes, system processes, interactive processes, and batch processes. Each queue has absolute priority over lower priority queues. No process in the batch queue, for example, could run unless the queues for real-time processes, system processes, and interactive processes were all empty. If an interactive process entered the ready queue while a batch process was running, the batch process would be preempted and we have to serve the interactive process. So this is an example of how we can use multi-level queues with creating a priority based on different process types. Normally, when the multi-level queue scheduling algorithm is used, processes are permanently assigned to a queue when they enter the system. If there are separate queues for foreground and background processes, for example, processes do not move from one queue to the another queue because we make that categorization. Since processes do not change their foreground or background nature, we said that, okay, these are background processes and these are foreground processes. So that processes has to wait on that queue based on their runtimes, lifetimes. We cannot change the nature of that process. This setup has the advantage of low scheduling overhead, but it is inflexible. The multi-level feedback queue scheduling algorithm, in contrast to that, allows a process to move between queues. The idea is to separate processes according to the characteristics of their CPU bursts. If a process uses too much CPU time, it will be moved to a lower priority queue. This scheme leaves IO-bound and interactive processes, which are typically categorized by short CPU bursts, in the higher priority queues. In addition, a process that waits too long in a lower priority queue may be moved to a higher priority queue. This form of aging prevents starvation, which we already described. In general, multi-level feedback queue scheduler is defined by these parameters: the number of queues, the scheduling algorithm for each queue, the method used to determine when to upgrade a process to higher priority queue, the method used to determine when to demote a process to a lower priority queue, and the last one, the method used to determine which queue a process will enter when that process needs service. For example, consider a multi-level feedback queue scheduler with 3 queues numbered from 0 to 2, as you can see from this figure. We have 3 queues on a multi-level feedback queue scheduler. The scheduler first executes all processes in Q0. Only when Q0 is empty will it execute processes in Q1. Similarly, process in Q2 will be executed only if Q0 and 1 are empty. A process that arrives for Q1 will preempt a process in Q2. A process in Q1 will in turn be preempted by a process arriving for Q0. An entering process is put in Q0. A process in Q0 is given a time quantum of 8 milliseconds. If it does not finish within this time, it's moved to the tail of the Q1. If Q0 is empty, the processes at the head of Q1 is given a quantum of 16 milliseconds. If it does not complete, it preempted and is put into Q2. Processes in Q2 are run on a first come, first served basis, but are run only when Q0 and 1 are empty. To prevent starvation, a process that waits too long in a lower priority queue may gradually be moved to a higher priority queue. This scheduling algorithm gives highest priority to any process with a CPU burst of 8 milliseconds or less. Such a process will quickly get the CPU, finish its CPU burst, and go off to its next I/O burst. Process that needs more than 8 milliseconds but less than 24 milliseconds are also served quickly, although with lower priority than shorter processes. Long processes automatically sync to the Q2 and are served in first come, first served order, with any CPU cycles left over from Q0 and 1. So this is how you can design a multi-level feedback queue. So these are design specifications, similar to these ones. We select the number of queues as 3Q. We assign scheduling algorithms for every queue. We said that Q0 will be run as round robin with time quantum 8 milliseconds. Q1 will be execute round robin in 16 time quantum, 16 milliseconds time quantum, and Q2 will serve as first come, first served. So based on that, we select the number of queues, we select methods for every queue, and then we define the methods for promoting to higher priority queues and demoting for lower priority queues. And this is how you can design a multi-level feedback queue using our prior knowledge. Any question? Last week, we introduced threads to the process model, distinguished between user level and kernel level threads. On most modern operating systems, it's kernel level threads, not processes, that are being scheduled by the operating system, because we have to schedule threads. User level threads are managed by a thread library, and the kernel is unaware of them. One distinction between user level and kernel level threads lies in how they are scheduled. On systems implementing many-to-one and many-to-many models, you can remember from last week, the thread library schedules user level threads to run an available lightweight process. This scheme is known as process contention scope, since competition for the CPU takes place among threads belonging to the same process. To decide which kernel level thread to schedule onto a CPU, the kernel uses the system contention scope. So we have process contention scope and system contention scope. The first one, process contention, we have to decide which thread of the same process will be executed first. On the system contention scope, we have to decide which thread will be executed on the real CPU first. So the competition for the CPU with system contention scope scheduling takes place among all threads in the system. Systems using the one-to-one model, such as Windows and Linux, schedule threads using only system contention scope. So on that case, we don't need process contention scope. Okay, we already provided a sample POSIX pthread program in last week with an introduction to thread creation with pthreads. We know that how we can create pthreads using POSIX library. And we said that we can use pthread APIs to set the scope of, let's say, scheduling. Now, we're going to highlight the POSIX pthread API that allows specifying PCS, which is process contention scope, or SCS, system contention scope, during thread creation. Pthreads identifies pthread scope process and pthread scope system. So using that, we can set the attributes of our thread, and based on that, we can choose how we are going to schedule that thread we already created using pthread API on POSIX library. And here we have an example. You can already remember that we used same scheme to create, let's say, threads last week. But here we also have some scopes. In the last example, we used the default attributes, but here we can set or get the scope of our thread using pthread scheduling API. And here we have the example for that program. Our discussion so far has focused on the problems on scheduling the CPU in a system with a single processing core. If multiple CPUs are available, load sharing, where multiple threads may run in parallel, becomes possible. However, scheduling issues become correspondingly more complex. Many possibilities have been tried, and as we saw with CPU scheduling with a single core CPU, there is no one best solution. Traditionally, the term multiprocessor referred to systems that provided multiple physical processors, where each processor contained one single core CPU. However, the definition of multiprocessor has evolved significantly, and on modern computing systems, multiprocessors now applies to the following system architectures. We have multi-core CPUs, we have multi-threaded cores, we have NUMA systems, and we have heterogeneous multiprocessing. We are going to discuss multiprocessor scheduling, but I think it's enough for this week. We can continue multiple processor scheduling next week. Before the closing this week, do you have any question? Sorusu olan var mı? Yok sanırım. O zaman bu haftalık burada bitirelim. Haftaya multiple processor scheduling ile devam ederiz. CPU scheduling'e. Muhtemelen çok uzun sürmez, nispeten erken bitiririz. Vaktimiz kalırsa, daha doğrusu kalan vaktimize göre bugün bahsettiğimiz scheduling algoritmaları üzerinden birkaç tane de örnek yapmaya çalışırız. Sorusu olan yoksa bugünlük kapatalım. Görüşmek üzere, hoşça kalın, kendinize iyi bakın.